Hi guys, this lecture is about the strategic approach to decomposing monolith systems and modeling microservices, which is fundamental for building scalable and flexible architectures. To achieve clean code and system flexibility, it is very important to understand and manage two key metrics, coupling and cohesion. These are fundamental principles that define how easily your system can adapt to changes, expand, and be maintained. So coupling answers the question, how much do chains in one class or component require chains in another one? High coupling means that components depend strongly on each other. Cohesion describes how logically connected things are inside one entity or model. It can also be seen as metrics that reflect the single responsibility principle, how much an object or model has only one reason to exist or to change. The general rule is keep coupling low and cohesion high. Let us look at an example to understand these concepts better. Okay, we have a class author that contains a list of all books, and the class book has a reference to author. This creates a tight coupling, but the goal is low, when components are maximally independent and know the minimum information about each other, which allows them to work independently. A good example of low coupling is when the class book contains only the author ID instead of full author object. In this way, chains in one class have minimal impact on others. Now about cohesion. For example, if the class author contains user business logic but also has methods for validation and sending emails, this shows low cohesion. It means change for several reasons, which makes it harder to maintain. The goal is high cohesion, when all elements inside a component are logically united and change for only one reason. For example, functionality related to email is moved to a separate email service, and work with photos is moved to an image service. Okay, understanding different kind of coupling helps to build more flexible and less dependent systems. We already know that coupling is a metric that shows how much change in one component of the system will require change in another. Our goal is always to reach low coupling, so that different part of the system can work and grow as independently from each other as possible. Let us look at different types of coupling, starting with those that are more manageable and ending with those that cause the biggest problems. So we have four types of coupling: domain, pass-through, common, and content. The first type, domain coupling. This happens when components are connected by one domain and work together to realize a certain business function. It comes directly from your business logic, when it is required that one component knows about other. For example, we have an order service, a service that creates an order, while creating an order includes several subprocesses, such as payment and reserve items in the warehouse. In this case, order service knows about the existence of payment and inventory service, because it orchestrates this activity. Next type, pass-through. This coupling refers to a situation where one service acts as an intermediary between two services. It receives data from one service and transmits it to another without using it or making any change to it. This type of coupling can create unnecessary dependencies and complexity in the system, as it introduces additional layers that do not contribute to meaningful functionality, but require the change if the data structure changes. In this scenario, order service sends a request to inventory service. But to finish the final operation, the delivery service needs some data that is not in inventory service, but is present in order. As a result, order service is forced to include this extra data in the message that is sent to inventory service, even though inventory service does not need this data at all. Inventory service only passes it through to delivery service. This type of coupling should be avoided. The reason is that inventory service at the same point knows about data for delivery service, which it does not need. This limits how inventory service can be changed and make refactoring or interface changes more difficult. With such changes, you must think about how they affect the data that inventory service only forwards, like pass through. Common coupling. Common coupling occurs when multiple services or components share responsibility for managing the same data. This often involves services sharing a common database or file store. Let's take a look at the diagram. The order service can set the order state to created or confirmed. The delivery service can update the order state to delivered. Both services directly access and modify the same database table to update the order state. Although it seems convenient, this approach can introduce significant challenges in system maintenance, stability, and overall architecture integrity. With this type of coupling, we may encounter issues. Tie coupling. Services rely on each other because they share the same database, making changes harder. Data integrity risks. Multiple services updating the same data can cause inequalities and conflicts. Reduced service autonomy. Services can't evolve separately because data structure chains must be coordinated. Increased complexity. As the system grows, managing access patterns and ensuring data consistency becomes challenging. Compromised fault isolation. Issues in one service can more easily propagate to other due to the shared data store. Scalability limitations. Common data stores can become bottleneck and slow down system growth. Okay, let's move on to content coupling. This type of coupling is considered the worst case scenario in terms of architecture, as it creates the highest level of dependency between components. Occurs when one service directly accesses or modifies the internal data structure or logic of another service. This creates a strong dependency between services, as changes in the internal implementation of one service can directly affect the functionality of another. Content coupling often manifests itself in service by passing certain APIs or interfaces to interact directly with each other's databases, memory, or internal processes. In this scenario, content coupling occurs in the following way. The order service directly accesses the inventory services database to check and update stock level when an order is placed, instead of using a defined API. The inventory service directly modifies the delivery services database to update the delivery status and assign courier details. And a few problems. Of course, tie coupling. Services depend too much on each other, so changing or scaling one can affect the other. Data integrity risk. Shared data can be changed in ways that cause mistakes. Versioning difficulties. Changes inside one service's data can break other services that use it. Reduced fault isolation. Issues in one service can easily propagate to others due to tight coupling. Complex deployment. Services need to be deployed together to work correctly, which makes the process harder. Performance bottlenecks. Many services using the same database can slow it down. Security vulnerabilities. Skipping services interface can avoid security checks and expose sensitive data. And once we have looked at all types of coupling, you may have a logical question: what is the difference between common coupling and content coupling? Common coupling involves shared access to global data, while content coupling occurs when one component directly accesses or modifies the data of another component, leading to even tighter interdependencies. Good. Let us move to the question: how do we split the domain model into software entities and do it effectively? For this, there is a great methodology, domain-driven design, or DDD. This methodology is very useful because it helps to separate components and entities while creating an intuitive and flexible architecture. The concept of DDD were introduced in the book by Eric Evans. His main goal is to help us define entity aggregates and, in fact, to understand what exactly should become a microservice in our system. DDD is based on 5 key criteria that we will go through: ubiquitous language, entities, value objects, aggregates, and bounding context. In essence, DDD helps us not only to split the system, but to do it in a meaningful way, based on real business needs and relationships. Continuing the talk about domain-driven design, we came to its foundation, ubiquitous language. This is not only a set of terms, but a whole conceptual system that you create together while discussing and modeling your domain area. The whole team, from business analysis to developers, must use the same terminology to avoid ambiguity and mistakes. This unites the people of one project, giving a common and clear understanding of all concepts. Ubiquitous language must be necessary and sufficient to describe your business logic. This means it should include all key terms that describe the processes and entities of your domain and at the same time should not contain extra concepts. Let us look at a common example that often happens in development, the concept of client. Imagine a big project, for example, a CRM system. Each department, like sales, marketing, finance, uses its own terms. For the sales department, a client may mean a company that already signed a contract. For marketing, it is a lead or potential client who only showed interest. Developers may call it a user who has login and password. And the finance department may call it a customer who actually made a payment. These differences in terminology and in the understanding of the same entity lead to chaos. If in one microservice client is an entity with ID, name, and contact data, but in another it is only a user login, then there appear misunderstanding between teams and departments. This also causes duplication of logic and data inconsistency, because each service starts to work with information about the same person in its own way. The consequences can be very serious: errors in data, difficult integration testing, and constant expensive refactor. This example shows if we do not agree on a clear and common definition of client and related terms like lead, account, or customer at the level of ubiquitous language, we will face problems at all stages of development and maintenance. Ubiquitous language must be necessary and sufficient to describe our domain model and unite all project participants with a shared understanding. Now let us look at entities and value objects, which are basic building blocks of the domain model, and each of them has its own unique role. Entities are objects that have a unique identifier and go through a life cycle. Their state can change over time. Even if all their attributes are the same, two entities are considered equal only if their unique identifiers are the same. In contrast, value objects are defined only by their attributes. They do not have a unique identifier and they are immutable and static. This means that if at least one attribute of a value object changes, it is already considered a new object, not a changed old one. Therefore, two value objects are considered equal if all their attributes are the same, no matter when and where they were created. To understand better, let us look at an example. For a bank account, the identifier will be the account number, for example, IBAN. Two bank accounts entities are considered the same if their account numbers are equal, even if other attributes like balance are temporarily not the same. A bank account is a clear example of an entity because its balance changes all the time, for example, with deposits or withdrawals. This shows its life over time. Now about the value object, money. Value objects are defined only by their attributes and do not have a unique identifier. For money, this is the amount and currency. If you have two money objects with the value like $50, they are considered the same because their attributes, amount, and currency are equal. Value objects are immutable. If their attributes change, this is considered a new object, not a modified old one. For example, if money changes from $50 to $100, it creates a new object money, $100, not a modified existing one. They can be replaced without consequences if their attributes are equal. If one money object with $50 is replaced by another money object with the same value, it does not change the meaning or state of the system. Aggregates are key for defining microservices boundaries because they encapsulate related entities and value objects, ensuring data integrity. In the context of domain-driven design, an aggregate is a collection of entities and value objects that are logically connected and are treated as a one whole. One object of this collection is the root entity, through which access to all other objects of the aggregate happens. The key feature of an aggregate is that all invariants, business rules, and integrity conditions related to this aggregate are inside it. This means that any change inside the aggregate must keep its internal consistency, and outside objects cannot change its internal state directly, but only through its root entity. Okay. An example where payment is the root entity of the aggregate, and other objects are inside its boundaries. First, payment is an entity because it has a unique identifier, payment ID, and it changes its state during the life cycle, from pending to success or fail. Now about the object inside the payment aggregate, payment attempt. Each attempt to process a payment can be a separate entity because it has its own unique identifier, attempt ID, its own state, for example, initiated, processing, declined, authorized, and it can change its lifecycle independently of other attempts inside one payment. For example, a user may try several times to pay the same payment, and each will be a unique attempt. If the user first enters wrong card details and the payment fails, but then tries again successfully, these will be two separate payment attempts entities inside one payment aggregate. Amount is defined only by its attributes, numeric value and currency, and it does not have a unique identifier. Whether objects are immutable. If the amount changes, a new amount object is created and the old one is replaced, not updated. Payment method. This object encapsulates all needed information about the payment method, which does not need its own identity or lifecycle. It is defined only by its attribute, like type, last four digits, or car brand. Okay, what is a bounded context? It is a clearly defined area where a certain domain model is consistent, coherent, and has its own unique terminology and logic. Even inside one organization, different groups of stakeholders may work with unrelated elements or see them from different perspectives. For example, the term of client may have different meaning for the sales, the support, or the finance departments. The main advantage of bounded context is the autonomy they give to team. These concepts open the hands so that the team can make decisions different from decisions at the organization level. For example, if at the company level Kafka is used for public communication, a team inside its own context may choose gRPC for internal communication if it's more convenient. Each microservice or group of microservices should ideally be placed inside one bounded context. This allows you to isolate problems and chains because any modification in one context should have minimal impact on others. It also simplifies deployment and monitoring because you manage smaller and more focused units. However, in real systems, there is often the question of shared entities that cross between different contexts. And here we have two main approaches. Move shared entities into a common microservice. For example, a user profile service may contain basic information like name, email, photo that different contexts need to access. In such a case, it is important to clearly define the owner of this service and the rules of interaction to avoid a dump of mixed logic. And the second one, split data and duplicate. If different contexts look at the same entity from very different angles, sometimes it makes sense to separate this data, keeping only the relevant part in each context. For example, a payment service may keep only payment information about the user, while the profile service keeps general data. This approach works well if the data can really be separated, so that one context does not constantly have to request data from other. Good. This slide shows a practical step-by-step algorithm for using the principles of domain-driven design to decompose a complex system into microservices. It will help you take a structured approach to modeling and making architectural decisions. The first one, describe the work of the system from the point of view of stakeholders. At this stage, your goal is to create the ubiquitous language. This means you must involve all participants who will work with or use the system, from warehouse workers and support staff to end users, to define one clear terminology for describing the business logic. Split the system into bounding context. This step is needed if different groups of stakeholders work with unrelated elements of the system or see them in different ways. For example, as we saw before, client means one thing for the sales and another for the finance department. Dividing into bounding context allows teams to make their own technical decisions inside their domain without worrying about others. Identify entities and value objects in each bounding context. At this stage, usually nouns from your ubiquitous language become entities. Group entities into aggregates. If updating one entity requires updating another at the same time, for example, changing updated at or modified at in a related table, then it is most likely part of the same aggregate. Split aggregates into microservices. And finally, after defining the main domain microservices, you define the necessary technical services such as API gateway, logging services, authorization, and so on. This algorithm helps you decompose your system effectively, considering both business logic and technical aspects. Good. Now let us move from modeling to decomposition. Decomposing a monolith is a key step in moving to microservices, and there are two common approaches that can be used in practice. The choice between these approaches often depends on the specific challenges you face during the migration of a microservice. Let's start. Code first. This approach is the default scenario and is used in most cases. The main idea is that we keep one shared database for the existing monolith and all new microservices. We focus on splitting the code. We take functionality out into new microservices, which now exist as separate entities, but still work with the same shared database. It is important that they do not share data directly at the code level. If a new microservice needs data that belong to the monolith or another service, it must send a request to the correct service to get this data and not access the database tables directly. The goal of this approach is to test if the code and business logic can be separated successfully from the monolith, and also to make sure that all existing constraints and functionality still work correctly in the new distributed setup. The second approach is data first. This option is used when you have serious doubts about splitting the data correctly. It is especially important if you are worried about losing data consistency without using foreign keys. This situation is critical, for example, in systems that process payments. This approach is also chosen if you are afraid that replacing database-level joins with program-level data joins in the microservice code will cause big performance problems. In this scenario, the first task is to migrate and split the data, and only after that each new microservice gets its own separate database, reducing the risks related to data. It is also important to take into account Conway's law, which shows the deep connection between the organizational structure of a company and the architecture of its systems. Conway's law is formulated like this. Any organization that designs systems will create a design with a structure that mirrors the communication structure within the company. Even if the architect designs a different system, over time it will still adapt and reflect the existing organizational structure and communication channels. This is easy to understand. The closer the team are physically, the better their communication is, and this directly affects the interaction of the systems they create. Like the organization defines the architecture, and the architecture supports the independence of the organization. In other words, with correct organizational planning, we get these advantages. Independent work. Teams work independently, are fully responsible for their results, and can choose technologies and implementation methods. Fast and independent releases. They can release when they need to, without being blocked by other teams, which speeds up the delivery of functionality. Clear accountability. If a particular feature is not working well, the responsibility lies with a specific team, which promotes faster problem solving and higher quality. Reducing coupling. A coordinated organizational structure reduces the need for additional approvals and joint meetings, allowing teams to move faster. So Conway's law not only describes the connection, but also gives guidance for designing the organization structure in a way that supports the desired microservice architecture and gives maximum development efficiency. Now we will look at transition patterns, and the first one is the strangler application. The name comes from the strangler fig vine. It grows around a host tree, step by step takes over its function, and finally completely replace it. The same happens in migration. We wrap the monolith with a routing shell, move parts of functionality into separate services, and step by step push out the old core. The idea is that we gradually take functionality out of the monolith and redirect traffic to the new service. This means that during the transition period, we have two subsystems at the same time, the new subsystem and the old one, like our monolith. The transition happens step by step, which allows us to release piece by piece. Users slowly stop using the old functionality and move to the new one. This greatly reduces the risks of big one-time migrations and allows testing the new services without harming the whole system. The final goal of this strategy is the full replacement of the monolith. The old system disappears over time. In this way, you get all the benefits of microservices architecture while avoiding critical downtime or a complete rewrite of the system from zero. Now, let us look at the anti-corruption layer, or ACL. This is a key protective barrier that is placed between the old monolith and new microservices. Its main goal is to stop the pollution of the new system with the logic of the old, so that the microservice architecture stays clean and independent. This pattern allows you to control the interaction in one central place between the new and the old system. For example, if some functionality like payments is moved from the monolith into a separate microservice, ACL allows you to update the traffic routing in one place instead of making changes in every microservice that talk to this functionality. ACL gives important flexibility during migrations. You can extend its functions and use feature flags to make more complex and controlled rollouts. For example, you can send traffic to the new microservice only for company employees, testing their functionality before releasing it for all users. In the simplest case, ACL can be done with Nginx, which only routes the traffic. In more complex cases, it can be built with custom logic. It is important to understand that the anti-corruption layer is a temporary solution. After the migration is finished and the monolith is fully replaced with microservices, the ACL is removed because its function is no longer needed. It is a bridge during the transition, not a permanent part of the target architecture. So now we have learned the approaches for modeling and decomposition. And now we move to an important question: how we to present our architecture. There is a great tool, C4 diagrams. They give a hierarchical way to show the architecture, which let us see the system at different levels of detail. This system is called C4 because it has four keywords, all started with the letter C: context, container, component, and code. The main idea is the hierarchical structure. Each next diagram is a more detailed view of a box from the previous diagram. It's like a zoom on a map. You can start from a high-level overview of the system and then go deeper step by step into the detail of its implementation. This makes C4 diagram very flexible for communicating architecture decisions both with technical experts and with business stakeholders, giving everyone the level of detail they need. In most cases, the first two levels are enough. The first and higher level of abstraction in C4 diagrams is the system context. At this level, we focus on one software system, the people, and the environment in which it works. This gives a general picture of the place of our system in the wider ecosystem. The key feature of this system context is that it's shown to all stakeholders. both technical and non-technical. Its goal is to give business users, managers, and engineers a shared understanding of what is valuable for the user and how your system interacts with the outside world. Because of its simpler but important role, this level is recommended to always create, since it's the starting point for any architecture decision and design. Moving to the second level of detail in C4 diagrams, we came to the container level. This level gives a high-level view of the architecture inside the system, showing the interaction between the main software elements. At this level, we focus on containers, which are the main runnable artifacts that make the system work. These can be separate services such as front-end and back-end microservices, databases, mobile apps, web apps, or even file systems. It is important to note that the word containers in C4 diagram means a logical container of code or data. This level usually matches the organizational structure, which makes it very clear for internal teams. The audience for this diagram is everyone involved in development, including engineers, architects, and technical managers, because it gives enough detail to understand how different parts of the system works together. Just like the system context level, this level is recommended to always build because it is an important bridge between the high-level business context and the detail of implementation. Moving to the third level in the C4 diagram hierarchy, we go deeper into the component level. At this stage, we add more details to the architecture, showing functional blocks and their implementation at the code level. The component level focuses on what happens inside one container. It shows high-level code abstractions such as controllers, repositories, and or models. This is not about specific classes, but about logical blocks that play a certain role in the system. This diagram is usually shown to technical people inside one team because it gives a deeper understanding of the internal logic and the interaction between main program abstractions. It is important to note that, unlike the system context and container levels, the component level should be created only if it brings real value in your case. This means it's not always necessary to build it, and it should be used only when the extra details really helps to understand or discover the architecture inside the team. And we have reached the deepest level of detail in C4 diagrams, the code level. Like the previous one, this level goes deeper into the architecture, showing functional blocks and their implementation, but now at a very low and detailed level. The code level shows what happens inside one component. It's usually presented as a low-level UML diagram of software entities and their relationships. Here we already see concrete classes, their attributes, methods, and connections, which is the closest view of the real code. This level can be useful when discussing the implementation of new functionality, when it is important to understand how exactly the feature will be built at the level of separate software entities. It is also often used for documentation of specific implementation details. One of the advantages is that IDE tools can usually generate such diagrams automatically, which make them easier to create and keep up to date. However, because of the high detail and possible complexity, this level is the most optional one and should be used only if there is a clear need. Okay, moving to the question of practical use of C4 diagrams, it is important to mention the recommended tools for creating them. Using specialized tools make the process of creating, editing, and supporting architectural diagrams much easier. One of the most convenient tools is diagram.net. In its search, you can simply type C4 and you will get special components made for this type of diagram. A similar tool is Lucidcharts. Another useful tool is Mermaid. It allows you to create simple diagrams with text description, which make them easy to version and integrate into documentation. There are also other tools such as IcePanel, Structurize, and PlantUML. In general, such diagrams are very valuable tools. They are useful for presentations, helping to visually explain complex architecture to different stakeholders. They are also effective for project documentation, giving a clear understanding of the system to all team members. With their help, it is easy to show who interacts with whom and the place of each service in the whole ecosystem. Let us also make a high-level overview of sequence diagrams, which are a very powerful tool for showing the dynamic of interaction between systems components over time. This is an important part of architecture documentation because it helps to understand how processes happen step by step in time. It is important to understand the place of sequence diagram among other types. All diagrams are divided into structural and behavioral. Structural, like the C4 we already know, focus on showing the structure of the system and the connections between its elements. In contrast, sequence diagrams are behavioral. Their main purpose is to describe the interaction between two or more services, especially when we need to have an explicit timeline to track the order or events. These diagrams allow us to clearly show the operation that happens between components over time. With them, we can show different logic combinations, such as conditions, which let the process branch depending on the situation, and loops, which show repeating actions. For example, this can be useful to show polling logic when a client asks the server for updates again and again. Each arrow on the diagram has a label to clearly explain what happens at every moment. In conclusion, sequence diagrams are a convenient tool for documenting complex interactions, especially in microservices architecture, where many services are involved. They help engineers quickly understand the flow of data and logic, without spending time figuring out who is calling whom. For visualization, we can use tools like PlantUML or Creately.com. Good. We have already learned why low coupling and high cohesion are the base of the flexible architecture. We saw how domain-driven design helps to create microservices in a meaningful way. We looked at two strategies of monolith decomposition, code first and data first. We mentioned Conway's law and how the team structure affects the system design. We also studied transition patterns like Strangler and ACL, which allow migration without pain. And for visualization of architecture, C4 and sequence diagrams, which give a clear picture for both business and technical teams. Here is a quiz about the material we studied today. And thank you for your attention and see you later. Bye bye.